The Pentium III brand refers to Intel's 32-bit x86 desktop and mobile microprocessors based on the 6th-generation PIII microarchitecture introduced on February 26, 1999. The brand's initial processors were very similar to the earlier Pentium II-branded microprocessors. The most notable differences were the addition of the SSE instruction set, and the introduction of a controversial serial number embedded in the chip during the manufacturing process. Processor cores: similarly to the Pentium II it superseded, the Pentium III was also accompanied by the Celeron brand for lower-end versions, and the Xeon for high-end derivatives. The Pentium III was eventually superseded by the Pentium IV, but its dual Latin core also served as the basis for the Pentium M CPUs, which used many ideas from the PIII microarchitecture. Subsequently, it was the Pentium M microarchitecture of Pentium M-branded CPUs, and not the netburst found in Pentium IV processors, that formed the basis for Intel's energy-efficient core microarchitecture of CPUs branded Core II, Pentium dual-core, Celeron, and Xeon. Katmai. The first Pentium III variant was the Katmai. It was a further development of the Destute's Pentium II. The Pentium III saw an increase of 2 million transistors over the Pentium II. The differences were the addition of execution units and SSE instruction support, and an improved L1 cache controller, which were responsible for the minor performance improvements over the Destute's Pentium IIs. It was first released at speeds of 450 and 500 MHz in February 1999. Two more versions were released, 550 MHz on May 17, 1999 and 600 MHz on August 2, 1999. On September 27, 1999 Intel released the 533B and 600B running at 533 and 600 MHz respectively. The B suffix indicated that it featured a 133 MHz FSB, instead of the 100 MHz FSB of previous models. The Katmai contains 9.5 million transistors, not including the 512 kB TESL2 cache, and has dimensions of 12.3 ohm by 10.4 ohm. It is fabricated in Intel's P856.5 process, a 0.25 micrometer CMOS process with 5 levels of aluminum interconnect. The Katmai used the same slot-based design as the Pentium II but with a newer SECC2 cartridge that allowed direct CPU core contact with the heat sink. There have been some early models of the Pentium III with 450 and 500 MHz packaged in an older SECC cartridge intended for OEMs. A notable stepping for enthusiasts was SL35D. This version of Katmai was officially rated for 450 MHz, but often contained cache chips for the 600 MHz model and thus usually was capable of running at 600 MHz. Coppermin. The second version, codenamed Coppermin, was released on October 25, 1999, running at 500, 533, 550, 600, 650, 667, 700, and 733 MHz. From December 1999 to May 2000, Intel released Pentium IIs running at speeds of 750, 800, 850, 866, 900, 933 and 1000 MHz. Both 100 MHz FSB and 133 MHz FSB models were made. An E was appended to the model name to indicate cores using the new 0.18I m fabrication process. An additional B was later appended to designate 133 MHz FSB models, resulting in an EB suffix. In terms of overall performance, the Coppermin held a slight advantage over the AMD Athlons it was released against, which was reversed when AMD applied their own die shrink and added an on-die L2 cache to the Athlon. Athlon held the advantage in floating-point intensive code, while the Coppermin could perform better when SSE optimizations were used, but in practical terms there was little difference in how the two chips performed, clock for clock. However, AMD were able to clock the Athlon higher, reaching speeds of 1.2 GHz before the launch of the Pentium IV. A 1.13 GHz version was released in mid-2000 but famously recalled after a collaboration between Hardock and Tom's Hardware discovered various instabilities with the operation of the new CPU speed grade. The Copperman core was unable to reliably reach the 1.13 GHz speed without various tweaks to the processor's microcode, effective cooling, additional voltage, and specifically validated platforms. Intel only officially supported the processor on its own VC820i820 based motherboard, but even this motherboard displayed instability in the independent tests of the hardware review sites. In benchmarks that were stable, performance was shown to be subpar, with the 1.13 GHz CPU equaling a 1.0 GHz model. Tom's Hardware attributed this performance deficit to relaxed tuning of the CPU and motherboard to improve stability. Intel needed at least 6 months to resolve the problems using the new CDO stepping and re-released 1.1 GHz and 1.13 GHz versions in 2001. Microsoft's Xbox game console uses a variant of the Pentium III mobile Celeron family in a micro PGA2 form factor. The S-spec designator of the chips is SL5SX, which makes it most similar to the mobile Celeron Copperman 128 processor. It shares with the Copperman 128 Celeron its 133 MTS front-side bus, 128 kb L2 cache, and 180 ANM process technology. Major improvements introduced with the Copperman were an on-chip L2 cache and better pipelining. The ATC operates at the core clock rate and has a capacity of 256 kb. It is 8-way set associative and is accessed via a 256-bit bus. These features resulted in a cache with a lower latency relative to CATME, improving performance significantly. Under competitive pressure from the AMD Athlon, Intel reworked the internals, finally removing some well-known pipeline stalls. The result was that applications affected by these pipeline stalls ran faster on the Copperman by up to 30%. The Copperman contained 29 million transistors and was fabricated in a 0.18 AA micrometer process. Although its code name gives the impression that it used copper interconnects, its interconnects were in fact aluminium. The Copperman was packaged in a 370-pin FCPGA for use with socket 370, or in SECC2 for slot 1. Early versions have an exposed die, whereas later versions have an integrated heat spreader to improve contact between the die and a heat sink. This in itself did not improve thermal conductivity, since it added another layer of metal and thermal paste between the die and a heat sink, but it greatly assisted in holding the heat sink flat against the die. Earlier Coppermans without the IHS made heat sink mounting challenging. If the heat sink was not flat against the die, heat transfer efficiency was greatly reduced. Some heatsink manufacturers began providing pads on their products, similar to what AMD did with the Thunderbird Athlon to ensure that the heatsink was mounted flatly. The enthusiast community went so far as to create shims to assist in maintaining a flat interface. Copperman T. This revision is an intermediate step between Copperman and Chulatin, with support for lower voltage system logic present on the latter but core power within previously defined voltage specs of the former so it could work in older system boards. Intel used the latest Coppermans with the CDO stepping and modified them so that they worked with low voltage system bus operation at 1.25 VA-GTL as well as normal 1.5 VA-GTL plus signal levels, and would auto-detect differential or single-ended clocking. This modification made them compatible to the latest generation Socket 370 boards supporting FCPGA2 packaged CPUs while maintaining compatibility with the older FCPGA boards. The Copperman T also had two-way symmetrical multiprocessing capabilities, but only in FCPGA2 boards. They can be distinguished from Chulatin processors by their part numbers, which include the digits 80,533, for example the 1133 MHz SL5QKPN is, RK80533PZ006256, while the 1000 MHz SL5QJPN is, RK80533PZ001256. Chulatin. The third revision, Chulatin, was a trial for Intel's new 0.13 AA micrometer process. Chulatin-based Pentium IIIs were released during 2001 until early 2002 at speeds of 1.0, 1.13, 1.2, 1.26, 1.33 and 1.4 GHz. Chulatin performed quite well, especially in variations which had 512 kbl2 cache. The Pentium III's variant was mainly intended for servers, especially those where power consumption mattered, that is, thin-blade servers. The Chulatin also formed the basis for the highly popular Pentium III mobile processor, which became Intel's frontline mobile chip for the next 2 years. The chip offered a good balance between power consumption and performance, thus finding a place in both performance notebooks in the thin and light category. The Chulatin-based Pentium III had shown superior performance compared to the fastest Willamette-based Pentium IV, and even the Thunderbird-based Athlons. In spite of this, it appears that Intel wanted to end the Pentium III's life, as they modified the Chulatin-based Pentium IIIs to be incompatible with the then-existing socket 370 motherboards and kept the L2 cache in non-Pentium III's models 256 KB. Moreover, Intel's only officially supported chipset for Chulatins, the i8-15T, could only handle 512 MB RAM and had inferior performance because of a fixed command queue depth of 1, compared to 8 with the older BX chipset. However, the enthusiast community found a way to run Chulatins on then ubiquitous BX chipset-based boards, although it was often a non-trivial task and required some degree of technical skills. Chulatin-based Pentium III CPUs can usually be visually distinguished from copper-min-based processors by the metal integrated heat spreader fixed on top of the package. However, the very last models of copper-min Pentium IIIs also featured the IHS. The integrated heat spreader is actually what distinguishes the FCPGA2 package from the FCPGA. Both are for socket 370 motherboards. Before the addition of the heat spreader, it was sometimes difficult to install a heatsink on a Pentium III. One had to be careful not to put force on the core at an angle because doing so would cause the edges and corners of the core to crack and could destroy the CPU. It was also sometimes difficult to achieve a flat mating of the CPU and heatsink surfaces, a factor of critical importance to good heat transfer. This became increasingly challenging with the socket 370 CPUs, compared with their slot 1 predecessors, because of the force required to mount a socket-based cooler and the narrower, two-sided mounting mechanism. As such, and because the 0.13 AA micrometer Chulatin had an even smaller core surface area than the 0.18 AA micrometer copper-min, Intel installed the metal heat spreader on Chulatin and all future desktop processors. The Chulatin core was named after the Chulatin Valley and Chulatin River in Oregon, where Intel has large manufacturing and design facilities. Pentium III's SSE implementation. Since Katmai was built in the same 0.25 AA micrometer process as Pentium II desktop, it had to implement SSE using as little silicon as possible. To achieve this goal, Intel implemented the 128-bit architecture by double-cycling the existing 64-bit data paths and by merging the SIMD-FP multiplier unit with the x87 scalar FPU multiplier into a single unit. To utilize the existing 64-bit data paths, Katmai issues each SIMD-FP instruction as 2i1/4 ops. To compensate partially for implementing only half of C/unregistered trademark S architectural width, Katmai implements the SIMD-FP adder as a separate unit on the second dispatch port. This organization allows one half of a SIMD multiply and one half of an independent SIMD add to be issued together, bringing the peak throughput back to 4 floating-point operations per cycle at least for code with an even distribution of multiplies and adds. The issue was that Kashmir unregistered trademark S hardware implementation contradicted the parallelism model implied by the SSE instruction set. Programmers faced a code scheduling dilemma: should the SSE code be tuned for Katmai's limited execution resources, or should it be tuned for a future processor with more resources? CATME-specific SSE optimizations yielded the best possible performance from the Pentium III family but was suboptimal for later Intel processors, such as the Pentium IV and Core. Core specifications. CATME, L1 cache, 16 plus 16 kilobytes, L2 cache, 512 kilobytes, external chips on CPU module at 50% of CPU speed, MMX, SSE, slot 1, VCORE, 2.0V, clock rate, 450 Euro 600 MHz, 100 MHz FSB, 450, 500, 550, 600 MHz, 133 MHz FSB, 533, 600 MHz. Coppermin, L1 cache, 16 plus 16 kilobytes, L2 cache, 256 kilobytes, full speed, MMX, SSE, slot 1, socket 370, front side bus, 100, 133 MHz, VCORE, 1.6V, 1.65V, 1.70V, 1.75V, first release, October 25, 1999, clock rate, 500 Euro 1133 MHz, 100 MHz FSB, 500, 550, 600, 650, 700, 750, 800, 850, 900, 1000, 1100 MHz, 133 MHz FSB, 533, 600, 667, 733, 800, 866, 933, 1000, 1133 MHz. Coppermin T, L1 cache, 16 plus 16 kilobytes, L2 cache, 256 kilobytes, full speed, MMX, SSE, socket 370, front side bus, 133 MHz, VCORE, 1.75V, first release, June 2001, clock rate, 800 Euro 1133 MHz, 133 MHz FSB, 800, 866, 933, 1000, 1133 MHz. Chulatin, L1 cache, 16 plus 16 kilobytes, L2 cache, 256 or 512 kilobytes, full speed, MMX, SSE, hardware prefetch, socket 370, front side bus, 133 MHz, VCORE, 1.45, 1.475V, first release, 2001, clock rate, 1000 Euro 1400 MHz, Pentium III, 1000, 1133, 1200, 1333, 1400 MHz, Pentium III's, 1133, 1266, 1400 MHz. Controversy about privacy issues. The Pentium III was the first x86 CPU to include a unique, retrievable, identification number, called PSN. A Pentium III's PSN can be read by software through the CPU ID instruction if this feature has not been disabled through the BIOS. On November 29, 1999, the Science and Technology Options Assessment Panel of the European Parliament, following their report on electronic surveillance techniques, asked parliamentary committee members to consider legal measures that would prevent these chips from being installed in the computers of European citizens. Intel eventually removed the PSN feature from Chulatin-based Pentium IIIs, and the feature was not present in Pentium IV or Pentium M. See also, Intel Pentium IV microprocessor, list of Intel Pentium III microprocessors, list of Intel Celeron microprocessors, references. External links, listing of various PII, PIII, and Celeron alphanumeric model designations, comparison of 7th generation x86 CPU architectures, Intel FAQ about the Pentium III processor serial number.